So welcome to this 14th episode of the online Spintronics seminar series. This is Kirill Belashenko from the University of Nebraska. Our speaker today is Professor Rembert Duine from the University of Utrecht. Professor Duine obtained his PhD in 2003 from the University of Utrecht. Then he had a postdoctoral appointment at the University of Texas, and then returned back to Utrecht as a professor. So he is a full professor since last year, and he also holds a partial appointment at Eindhoven University of Technology, at NTNU and QSpin. He'll talk today about geometry and topology and in magnetic dynamics. Please welcome Professor Duine.
Thank you. Thank you for the nice introduction. So first of all, I'd like to thank the organizers for putting together this nice seminar series right on time. So I've not been joining a lot in the evening, but I've developed, as many of you, or at least some of you probably know, I'm a keen bicyclist, and so I've been watching quite a bit of seminars, the recordings in the morning, while sitting on my bike in our shed. So this morning I was watching last Tuesday's seminar. As you can see here, if you look closely, my heart rate is 124. That could either be because of the cycling or because I was excited that Greg was referencing our work. But this has been kind of a nice combination of work and pleasure, so to say, to watch seminars in the morning in the shed on my bike. Okay, so I'll be talking about geometry and topology and magnetic dynamics. This is, of course, a very broad topic, and will not touch upon kind of an overview of it, but I'll rather discuss some examples of work that we've been doing recently, mostly on geometric phases in magnetic dynamics. And at the end, I'll talk a little bit about topology, but mostly giving you a teaser for Benedetta Flavis's talk, which was the second of this series and is recorded online, and you can look for the details there. But I'll give hopefully a teaser for that work there. I'll be discussing most of what I'll be discussing is in these papers. So the first part of the talk will be about geometric phases, and I just want to give you, to start off with, I want to give you an example that highlights, I think, what the power is of geometric phases or why they're useful. It's a little bit of a, let's say, academic example, so I do want to encourage my experimentalist colleagues who are listening, watching hopefully, to think how to do it experimentally, but this is not intended to as a recipe for experimentalists, but rather as an example that shows some of the features. So what I'm looking at for the first one, part here, is two single domain ferromagnets coupled via an exchange coupling that can be ferro or antiferromagnetic. So there's two single domain magnetizations on the left and on the right. These vectors point in the direction of magnetization, ML and MR, and they're subject to an effective field on the left and the right, and there's a field gradient. So there could be a difference in anisotropies or a difference, let's say, gradient in applied field that is different between left and right in this setup. So most of for this example, I'll be discussing a situation that, let's say, the coupling is weak, such that let's say the state or the ground state is determined by the effective field and is always pointing parallel. Just to be definite, let's say an example of an energy for this system would be just field on the left, field on the right, and then an exchange coupling between the left and the right, as written down here. And so for the time being, I'll ignore actually dissipation. So both of these magnets are subject to recessional dynamics as described by the Landau-Lifshitz equation, not even the Landau-Lifshitz-Gilbert, just the Landau-Lifshitz. just precession around these effective fields HL and HR. Here. So I'll ignore damping for this first example. I'll work towards damping, inclusion of damping later on. And so let's now ask ourselves the following question. So let's imagine that we have this setup. Initially we take this coupling to be 0, and we take, let's say, the left effective field to be larger than the right effective field, and we just excite this left magnet. So I don't mean continuously exciting, but we just excite it once, meaning we tilt it away from its equilibrium direction, so it will start precessing. And since we are neglecting damping for the moment, this precession will just go on forever. Energy is conserved. And what I now imagine doing, and again, I don't mean to challenge my experimentalist colleagues to actually do this, but just as a Gedanken experiment, a thought experiment, what I now imagine doing, so starting from the situation that this left magnet is precessing around this effective field, which is larger on the left than on the right. We now imagine slowly changing in time the coupling between these two single domain magnets, and also slowly changing the field gradient, meaning the relative magnitude of the field on the left and on the right. Okay, so there's a parameter space I've sketched here on the right. So there's exchange coupling, and this is the difference between fields on the left and on the right. And so let's now imagine that we slowly change the coupling from 0 to, let's say, the ferromagnetic case, so to the right of this axis here, and then at the same time decreasing the difference in field such that it becomes negative, such that this one has the larger effective field. And then basically in this phase, so in this parameter space, I should say, of exchange coupling and field difference or field gradient, we make a loop like this. And so the end result, and so we do this all very slowly, meaning that there are many cycles of precession of these two magnets while we're actually changing these parameters slowly. And so what will happen physically is that, let's say, so we started out with this left magnet precessing, we excited it, and we switch on the coupling. So part of its energy will be transferred to the magnet on the right, which will now also start precessing. And then when the coupling is finite, both of them are precessing. But then at the end, I transfer, since at the end I end up in the same situation as where I started, meaning that the left magnet is uncoupled from the right magnet. And so basically I should end up with only the left magnet precessing. So what happens in this time dependence is that I transfer the energy from left to right by coupling them. I play a little bit with the fields, the time dependence of the field, but in the end I end up with a magnet that's precessing on the left only, because I end up in the same situation as where I started. So I make this loop in parameter space. Now a question that you can ask yourself is what is now the phase difference between this initial precession of the left magnet and the final precession, or a little bit more precise, what would be the phase difference if I would not change the parameters in time in this particular way, but if I would do nothing, then the magnet on the left is precessing. And if I compare that situation with where I actually did this entire let's say protocol, so then I also end up with the left magnet precessing. You can ask yourself the question, what is now the phase difference, or the difference in precession angle between this initial and final precession? And when I gave this talk for my group last week, I scheduled it just to make sure that I had my slides ready for this talk in time, just to force myself. A lot of people gave the correct answer. So I don't know if you've been thinking about it, but the correct answer is that this phase difference is pi. And the nice thing about it is that this is always pi, provided that this change in parameters, this loop in parameter space, is traversed slowly enough. So again, slow means that there are many cycles of precession as you change these parameters adiabatically. So it doesn't really matter precisely how you, let's say, how you traverse this loop, as long as you kind of make a circle around the origin of the space of these parameters, and as long as you do it adiabatically. So it doesn't really matter how fast you do it, provided you do it slow enough. But then you could first actually, let's say, make J larger than 0, wait for a while, then continue in this loop, wait for a while, and then at some point go back. Or you do it kind of continuously all the way around. In all situations, this phase difference will be always pi. And so this is an example of a geometric angle or phase. It's actually called a Hannay angle. I will tell you later what those are in comparison to geometric phases in quantum mechanics that you may have heard about. And so it's independent of details of how you do it, and it's very it's robust in the sense that the details of how you traverse this loop don't matter. Now, why it is precisely pi, I leave up to you to figure out. So it's not the kind of this is just intended to be just an example of a geometric angle. You can find the answer by just like taking your favorite LLG or LL in this case, Landau-Lifshitz code, and just implementing this protocol, and then convincing yourself that this phase difference is indeed pi that you obtain. So everything I say is contained in the LLG, but you can also, of course, try to compute this phase difference by kind of rewriting cleverly the LLG, and then at some point you will find out that this delta phi is really a geometric property, meaning, and again, this is the definition of geometric in this part of the talk, that it depends not on precisely the time dependence of how this path in this case is traversed, but it depends only on the geometry of the path. Okay, so again, this is an example of a Hannay angle. I will come back to that in a second. And the reason it's always pi is that, okay, ultimately, actually, this example maps to a spin 1/2 Berry phase. So this entire problem, at least if you linearize it, maps to a spin 1/2 Berry phase that some of you are perhaps more familiar with than geometric phases in classical mechanics. So why? So this is, let's say, a Gedanken experiment. So some people may think about how to execute this, but it's very hard, of course. However, so this is an example of a geometric angle or geometric phase in the time domain. So it results from adiabatically changing, slowly changing parameters in the Hamiltonian or in the energy adiabatically slowly in time. You can always, at least almost always, transfer this situation to position-dependent parameters. And that actually becomes more useful, let's say, in the context of magnetization dynamics, and particularly in the context of spin waves. So let's now imagine that we don't do things in a time-dependent way, but we have a setup whereby we have, let's say, a wire with some ring-shaped structure connected to some ring-shaped structure in the same in the middle, and then some wire on the right here. And let's now imagine that everywhere this wire is made up of this synthetic antiferromagnetic material. So there's a top. So this everywhere this flat this thin film is composed of, let's say, 3 layers, non-magnetic spacer in between magnetic layer and magnetic layer, and that the fields and the magnetizations are pointing in the plane of the layer. And let's now imagine that rather than having a time-dependent change of parameters, we actually have a position-dependent change of parameters. So let's say that the effective field, this HL, and this could be due to anisotropy only, it doesn't have to be an external field, could be anisotropy, is actually position-dependent as we go along this wire, and the same for the bottom layer. So previously I had time dependence here, and now I have position dependence. And let's imagine that the anisotropies or these effective field change in such a way that as I encircle this ring here of thin film synthetic antiferromagnetic wire, as I encircle this this ring here, that the parameters, so again the exchange coupling between the 2 layers, J here, and the effective fields, they basically make the same loop in parameter space as I've shown before. So on the right here of the ring, the coupling is ferromagnetic. On the left, it's antiferromagnetic. And then say if you go around this ring, the effective fields change from the top one being the larger one to this top end here, and the bottom one being the larger one at this bottom end here. So as I go around this loop here, the parameters change in the way as sketched in this figure, which is identical to the previous figure, but here it's a change in let's say position space rather than in the time domain. And what this now basically means is that if I would send in a spin wave from the left, that this spin wave would impinge on this ring and would split into two. And let's say the phase difference with which the spin wave that takes the left hand path arrives at this point of the circle of the ring, with respect to the phase difference of the spin wave that takes the right hand path. So this phase difference will always be exactly this same pi that I discussed before, because these spin waves will pick up a geometric phase, so a phase that is related to the geometry of how of the path of in parameter space that the parameters take, so that the anisotropy and the field gradient, sorry, that the effective field gradient and exchange take as you go around this path. And so this phase is very robust, and it's always exactly pi. So these spin waves will always destructively interfere when they go around the ring here. However, if you apply an actual large field in the plane, then you basically make the field gradient negligible as compared to the applied field. And then you basically move this circle away from the origin. So you move it all the way up here. So, and then actually this destructive interference will be gone. There will be no longer a geometric phase that these spin waves pick up. And so this would allow you to build let's say a switch for spin waves. So without applied field, if this would be only anisotropy, there would be destructive interference, and with applied field, there would be constructive interference. Now, this is an example where you go from the time domain, which is, I think, very hard, to this position domain, which is also very hard, but perhaps less impossible than in situ in the time domain, changing all these parameters. Since you can kind of spatially engineer interface properties that determine anisotropies and the exchange as well, and you can play a little bit with the width of this metallic space in between. So this is, I'm not saying this is doable right away, but at least this doesn't look too impossible. But perhaps you can we can discuss this at the end of this seminar. Now, what I hope that this example of the synthetic antiferromagnetic nanowire shows is that so these geometric angles and topology I haven't discussed yet, but these geometric angles, they provide a robust way to understand and then also manipulate the magnetization dynamics. So what I mean with understand is that, so everything I've told you about so far is kind of can be obtained from the Landau-Lifshitz equation. However, if you would let's say solve the Landau-Lifshitz equation for this geometry and you wouldn't know about the existence of geometric phases, then you would be surprised all the time by the phase difference of pi exactly on this side. However, if you dive into it and actually try to compute this phase difference and actually conclude at some point that's really a geometric property of the spin waves that is related to the geometry of this path in parameter space, then this provides a useful way to understand it, and also immediately leads to the result that it's robust and therefore can be used to robustly manipulate this, in this example, these spin waves. Of course, if you manage to do this. Okay, so this was an example to kind of highlight what I think are the main nice features about this. And so the rest is kind of a little bit more examples, and I'll also talk about spin torque oscillators, in which case actually dissipation and nonlinearities are very important. And we'll actually see we get a new type of geometric phase in that system, that is not a Hannay angle as in this system. So this is kind of the outline of the rest of the talk. So I'll give a little bit more, let's say, details on these Hannay angles, and I'll discuss kind of some generic features of these geometric angles. So this first topic is not very new in the sense that people have been talking about things like the magnon Berry phase for quite a while. But I think this puts it in a nice perspective. And we'll also have an application that is perhaps slightly different from what has been discussed before. And then I'll switch to spin torque oscillators, where we also found a nice geometric phase. So I'll discuss how to imprint like in a robust way, a phase difference on a spin torque oscillator. And then at the end, I'll discuss arrays of spin torque oscillator, but this last part will be rather brief. And again, is mostly meant as a teaser for Benedetta Flevis's talk, which is recorded and which you can, if you haven't seen it yet, I hope to attract you to looking at that talk, as there are more details in there about this last part. So just to give the collaborators, so this is Andreas Rückriegel, with whom I worked on these geometric phases in magnetization dynamics. Andreas was a postdoc in Utrecht and is now a postdoc in Frankfurt in the group of Peter Kopietz. So Benedetta, some of you, if not all of you, know her. She's a postdoc now in UT Austin and will move to Boston College at the beginning of the academic year. And then Hilary Hurst, she is now a postdoc at NIST in Maryland, and she will move to San Jose later. And so I should also acknowledge, it's actually not in the slide, I should also acknowledge the Kavli Institute of Theoretical Physics, where most of this work, especially the work with Hilary and Benedetta, was at least conceived, where we had a very nice time with a large group of people. Probably several of you are in the audience, and especially at these times, the KITP is really is missed very much, at least by me. Okay, so again, I'll first discuss a little bit further these Hannay angles. So here's an overview of let's say the difference between Hannay angles and Berry phases. So on the left, Hannay angles and Berry phases. So in a nutshell, Hannay angles are the classical counterparts of Berry phases. So probably some of you are familiar, many of you are familiar with Berry phase, but Hannay angles are not so well known. So Hannay angles occur in classical integral systems, and the reason you need actually it should be confined classical integrable system. So basically, the reason it should be confined and integrable is that you need some periodic motion of the classical system to be able to define a phase of something. So the simplest example is just a particle moving in 2 dimensions, then the let's say the angular momentum out of the plane is conserved, and you can parameterize this with an angle and with the angular momentum itself. Those are 2 canonically conjugate variables. And then the angle will be a periodic, the angle around, let's say, the origin in the xy plane will be a periodic variable that in principle could pick up a geometric contribution if you very slowly change the parameters that describe this system. Now, since they are classical, they are directly observable, of course. So also in the previous example, in principle, magnetization is directly observable. So the phase of magnetization dynamics is directly observable. Of course, it can be very hard, it can be too fast, etc. But there's nothing in principle that prevents you from observing it. And this is contrary to Berry phases, which you can only observe through interference. And I usually this is a slightly technical point. So usually these Hannay angles are discussed in terms of so-called angle variables. So these are the variables that describe the periodic motion. Again, in the case of motion in the xy plane, this would be the angle around the origin, say, in the simplest case. That would be the angle variable, a periodic variable that is conjugate to some conserved quantity. That's typically the action variable. So in this case, the angular momentum. But these quantities don't have to be kind of the physical conserved quantities like energy or angular momentum. They could also be specific conserved quantities that are conserved for the specific change in parameters that you have in mind. And then, okay, if you have such a system which undergoes periodic motion, then if you do some adiabatic change in parameters, this angle that describes the periodic motion can pick up a geometric contribution. Again, a contribution that doesn't depend on how fast you change these parameters. If you change them slowly enough, you will get something that depends only on the path in parameter space and not on how fast it is traversed. That again is what I mean with geometric. Now the canonical example is actually the Foucault pendulum as sketched here, where you have periodic motion. Obviously it's a pendulum, so there's an angle you can associate with that, with the angle in the XY plane, say, of this pendulum. And then since the Earth rotates, the parameters, namely the gravitational field, etc., and the, sorry, not the gravitational field, the Coriolis force, gives some time dependence and actually leads to a change in the plane of rotation of this Foucault pendulum. And this change in plane of rotation as the Earth revolves, let's say in one day, or one day and one night, is actually can be expressed as a geometric phase. So it's purely geometric. If the Earth would rotate twice as slowly, it would still be the same change of plane of swinging, say. Okay, so that's and funnily enough, this Foucault pendulum is actually often advertised as an example of a Berry phase, but it's really an Hannay angle. Now, just to contrast quickly with Berry phases, so they are obviously quantum mechanical. You can observe them only through interference. They are, let's say, a result of solving the Schrödinger equation adiabatically, and then there's a geometric phase of the entire wave function. What's also interesting is that the Berry phase paper has, let's say, 10,000 citations, give or take, whereas the Hannay angle paper has 650 citations. Now, there are various interesting relations between the Hannay angle and the Berry phase, and I invite you to explore, in particular, this book about it. Now, what about Hannay angles in magnetization dynamics? So as I said, often it's very convenient to express dynamics if you want to extract a geometric phase in terms of an action variable that is conserved and an angle variable that is describing the periodic motion that you're looking at. And then these two equations basically always hold. So the action variable should be conserved, but since they're conjugate, it's also the derivative of the energy with respect to the angle variable should be zero. And then basically the periodic motion, the frequency of that is described by the derivative of the energy with respect to the action variable. So think again in terms of an example of angular momentum in the z direction and then angle around this direction. And so if you want to compute now the geometric phases associated with magnetization dynamics, you first need to identify what are these action and angle variables. And the angle variable is rather simple. It's just the precession angle. And so let's look now at magnetization dynamics on the unit sphere. So here's the unit sphere. So there is some external field pointing in the direction capital N, and then magnetization is precessing around this external field. And in general, this precession is elliptical. And so here's a top view of this precessional motion. So the precession is elliptical. I'm looking, let's say, straight on top of this vector N. And so this precession is elliptical and is characterized by an angle phi, which will be the angle variable of the magnetization dynamics. And now just to be concrete, since a lot of this depends precisely on choice of anisotropies, energy, and so on, I want to choose a very simple toy model that allows one to do the anatomy of the geometric phase in a very neat way, I think. So there's just an external field in the direction N. And then there are two hard axis anisotropies that give energy cost for tilting away from the easy axis, which is N. And so they basically describe the energy cost for tilting away from the external field. So the anisotropy basically rotates with the external field such that the precession is always elliptical around the external field. But precisely how this ellipse is shaped depends on an angle phi that describes how this ellipse is oriented, how the anisotropy axes are oriented with respect to the external field. And again, this is of course in the time domain to do this very, very hard, but I'll come to an example for spin wave interference that may be actually achievable experimentally. Okay, so the point is I have an external field in some direction N, and then the magnetization is precessing around this external field on an ellipse, and the orientation of the ellipse, so the anisotropy axis, how they are oriented is determined by an angle phi. So the anisotropy axis depends on this angle phi. And what I'm going to do is I'm going to make both the external field and the anisotropy axis time dependent. I'm going to be interested in now if I do a circular change, let's say a periodic change of the external field and of the anisotropy angles, if I then get a geometric phase shift in the precession. Now to compute this, you have to rewrite it in terms of action and angle variables. The question is now, what is a good action variable? And it turns out to be the area of the ellipse for this particular energy. So if whatever I do, provided I do it slowly enough, so provided I change the external field and the anisotropy axis slowly enough, the area of this ellipse will always be conserved. Okay, so I will not go through the technical details, but so what we did is we computed the geometric phase. And so we imagine we rotate the principal axis of the anisotropy to determine how the ellipse of precession is oriented periodically. So they're characterized by this angle phi. We also change the external field periodically. So at least we do one, let's say, cycle in parameter space. So we change in a certain way. It's parameterized by these angles. And what you can then do is compute the geometric phase. And again, this is no magic. This is contained in the Landau-Lipschitz equation, but using this formalism by Hannay, you can compute it in a very neat way, I think. And then you get this contribution to the geometric phase. Okay, so this is as two contribution, one due to the change of anisotropy, so that due to the, let's say, rotation of the precessional ellipse, and one due to the path that the field sweeps out on the unit sphere. So here are the two contributions again, and so here is now, let's say, let's imagine that the external field has changed, so it's changed periodically, so it swipes out a certain solid angle on the unit sphere. And it turns out that if you would not have any ellipticity, this would be the ordinary, so the geometric phase would be the ordinary phase that you get for, as some of you know, that you get for parallel transport of a vector. So if you don't have any ellipticity, so these frequencies here, they determine how elliptical the precession is. So if the frequencies omega 1 and omega 2 that are related to the anisotropies along both hard axes, if they're equal to each other, then this factor becomes 2, and then the precession becomes circular. And then you can actually rewrite this contribution due to the adiabatic change in field. You can rewrite it as the solid angle enclosed by what you trace out on the unit sphere with the external field. However, if the precession is elliptical, you can no longer do this. You get a correction to this, so the prefect, you get a correction, but you also get an additional contribution. So this ellipticity comes with its own geometric phase. So if the ellipse of precession is slowly changing in time by changing the axis of the anisotropy, you get an additional geometric phase contribution that vanishes if the ellipticity is not there, but it should be taken into account if you have both, if you have ellipticity of precession. And if you want to get rid of it, what you have to do is apply a very large external field, because if you have a large external field, then the precession becomes more and more circular, and you get rid of this ellipticity of the precession, basically. Okay, so now this is again in the time domain, so that's maybe useless to actually implement experimentally, but you can do something again with, I believe, with spin wave interference. So what you can do is, for example, imagine that you have a wire along which the anisotropy change, let's say the directions of the anisotropy change as you go along this wire. And this you could in principle do by making this device. So let's imagine that that we have this device, so a thin film with again a circle, let's say a circle in the middle, a ring in the middle, I should say. And if the external field is pointing out of the plane, so if this is all magnetized out of the plane, then the shape anisotropy will cause the ellipse of precession to be different here, differently oriented, let's say here, and will adiabatically change as you go around this circle. So as you go around this circle, if you would have shape anisotropy, then you basically already get a situation where you make an adiabatic adiabatic now in space variation of the anisotropy. And so if you would send a spin wave from the left, then the geometric phase due to the change in ellipticity will be picked up by this spin wave in a different way than by the spin wave traveling on the right of this ring. And there could again be destructive interference between spin waves taking the left-hand path and the right-hand path, so to say. And so this is what we computed. So here you see a spin wave transmission as a function of frequency. And so there are two curves in this plot. So one curve is the dashed line. So that's the situation without the geometric phase. And then you really have to throw it out by hand, because in principle, the LLG or whatever approach you take to compute the transmission of this of spin waves in this rank structure, it will have the geometric phase in there, although perhaps not as explicit if you don't know about it. And so this will, so if you throw it away by hand, you get some oscillations, but you don't get this full destructive interference that you see here for spin waves that have the right frequency as they, and that is the result of this geometric phase. So the solid lines is the full calculation without throwing away explicitly this geometric phase. Before I forget it, I should point out that so this is all this spin wave, let's say this Hannay angle, as I now call it, this geometric contribution to the spin wave dynamics is basically the same as what people refer to as magnon Berry phases, even though I believe it's more popularly called a Hannay angle because it has to do with classical dynamics. And usually this distinction between, let's say, which part of the angle is due to ellipticity and due to the change in direction of effective field is not always made appropriately. Okay, so that's about let's say spin wave transmission and magnetization dynamics without dissipation. So you can ask yourself the question, what about dissipation? So if you add a tiny amount of dissipation, let's say by means of a Gilbert damping in the Landau-Lifshitz equation, you get a dephasing time of the periodic motion. So you'll observe the, let's say, these interference effects, or let's say the phase will be washed out over a time given by that's inversely proportional to the Gilbert damping and the frequency of precession. If you turn this into a length, so for the spin wave transmission that I discussed about, you'll have a dephasing length that's, let's say, in the order of the velocity of spin waves times this dephasing time. However, we know that, let's say, in magnetization dynamics, and then specifically in magnetization dynamics with spin torques, we often are very much interested in dissipation versus gain, so trying to balance the Gilbert damping by injecting spin. And so the question is now, does any of this physics of geometric, the question that we asked ourselves is, does any of the physics of these geometric phases survive in the presence of spin torques and when I have dissipation and gain? And the most, let's say, paradigmatic example of such a system that has this balance between dissipation and gain are spin torque oscillators that many of you, at least some of you, are perhaps more familiar with than I am. So the basic system is now we again have a single domain ferromagnet, so as shown here. And a single domain ferromagnet can precess around an external field and also has an effective field. Here I take only into account the shape anisotropy, say uniaxial anisotropy. And it has dissipation, so Gilbert damping, but on top of that, there's spin current being injected. So that gives rise to a spin transfer torque that can counterbalance the dissipation. And if you do that efficiently enough, if you overcome the intrinsic damping, you can get this to a precessional auto oscillation. And this is usually described in terms of a power that gives the intercept of the magnetization with the z direction. So if the power is 0, system is thus pointing in its equilibrium direction. If I then inject enough spin transfer torque, you can get it to this oscillatory motion at non-zero power, and then this angle phi is time dependent. Okay, so just some equations for completeness. So this is described, so from the Landau-Lifshitz Gilbert equation with this spin transfer torque, you can derive equations for the power. So how much the magnetization is tilting away from the ground state, say, and for this angle phi. So these are nonlinear equations, no approximations, say here. Typically, at least you don't need to make approximations. And so the power has two contributions. There's a loss term, this gamma plus, so this is a positive damping term. This is due to the Gilbert damping as described here, but also including nonlinear corrections because the LLG is in principle nonlinear. And there's an anti-damping contribution that is due to the spin transfer torque. So the spin transfer torque here is characterized in terms of a function g that depends on details of the spin transfer process, let's say. And these equations are obtained by going to quadratic order in P, which is very common in describing spin torque oscillators. And the frequency is nonlinear, depends on the anisotropy in this way. And if you compute when the power becomes non-zero, you get this critical current here that describes the balance between spin torque and dissipation. And so, so here's now a phase diagram. Let's say, so this is spin current, IS, so that's controlled by charge current depending on the implementation. And here is external field, omega 0. So this omega 0 is proportional to the external field. And so the critical current is drawn here. This is the critical current as a function of external field. So if the field is large, you need more current because the precession is faster. So above this line here, you have auto oscillations. The spin torque oscillator is precessing, and below here, it will be just pointing in the z direction. And now again, thinking about these geometric phases. So these are phases that arise because of adiabatically and slowly changing parameters here. So the natural parameters to change are the current as expressed in the spin current and the external field. So what you could imagine is that you start out in this processing state, let's say here, and then you basically slowly adiabatically make a loop in parameter space that should always be above in this let's say supercritical regime. So the spin torque oscillator is continuously processing. However, the phase of this precession will change, of course, as you change the parameters. And the question is now, if you go back, make a loop in this parameter space and go back to this original point here, is there now a geometric phase shift? So is there a phase shift that is very robust, doesn't depend on any details, and could be used to imprint, let's say, a phase shift on the spin torque oscillator? And the answer to that question turns out to be yes. So there is actually a geometric phase. So this is a geometric phase that is the result, that is kind of a specific example of a geometric phase that was first discussed by Landsberg already some time ago. So the geometric phase is non-zero, and you can express it as a integral over some field that is doesn't have anything to do with the actually applied magnetic field, but has this more complicated expression. So I don't want to go into detail, but basically the take-home message is that there is a geometric phase. It's non-zero, and it's not at all related to this Hannay angle, to this adiabatic dynamics when the energy is conserved. So it's a very different type of geometric phase. So as you can see here, it depends on both the spin torque via this G here. It depends on the dissipation alpha. And so it's not at all related to anything like this, the magnon Berry phase or the Hannay angle, if you will. So the question is now, what can we use it for? So first of all, a couple of remarks. So it generalizes to other implementations of spin torque oscillators. So it also exists for oscillators array, the geometric phase. It's not swamped by thermal fluctuations. We estimated the effect of thermal fluctuations, and you can observe it easily on top of thermal fluctuations. And there could be some applications. So I don't want to be too speculative here. I'm also not an expert in applying spin torque oscillators. But you could think that for applications where you actually need to control the phase of these spin torque oscillators, such as imprinting a phase on, if you use spin torque oscillators for exciting spin waves, you could imagine that you could use this geometric phase to imprint well-defined phase shifts on spin waves, for example, or any other applications that you may have in mind for your spin torque oscillator, at least on the basis of the phase. So I think I'm almost basically out of time. So let me, the last part I will just show you 2 slides and then a teaser slide for Benedetta Flebe's talk, and then I will be done. So this is about array of spin torque oscillators. So let's now imagine that I put 2 spin torque oscillators in an array, and then couple them weakly antiferromagnetically and inject spin current only in the left one, and do this above the critical current. And the question is, which one of these 2 oscillators starts actually oscillating if I exceed the critical current? And the answer is obviously the left one, on the left here, because that's the one that I inject the current in. You can ask this question also for an array of spin torque oscillators. So here I just have drawn 6. I could have also have drawn 100. Well, I couldn't actually, but let's imagine that there are 100 that are coupled antiferromagnetically. But I inject spin current only in every other one. So now you can also ask the question, which one starts auto-oscillating if I exceed the critical current? And the answer is the one on the left here. And none in the middle does anything. Also none on the right, none of the other ones starts oscillating. If I inject spin current in the other ones, the one on the right is the only one that starts oscillating. Now, why is this so? So this turns out to be related to, this turns out to be a manifestation of a edge mode that is protected by non-hermitian topology. And this is precisely what Benedetta's talk is about in more detail. So this is again an example, I think, a nice example of robust, in this case, topologically protected magnetization dynamics, where you don't need to know any details of the system to predict that only one oscillator starts oscillating, even though the actual magnetization dynamics that you might expect could be much more complicated, but turns out to be very simple in this case. So please check out Benedetta's talk about this. That contains more details about this. So let me finish by putting the take-home message again. So I've shown a couple of examples of how to understand in a robust way using these geometric angles, or to control in a robust way magnetization dynamics, particularly phase shifts of oscillations in a spin torque oscillator of the precession in a single domain magnet, and given some hints for perhaps applying this in terms of spin wave interference, or in terms of controlling the phase of a spin torque oscillator. So thank you for your attention.
Okay, thank you very much for this interesting talk. So we can now take questions. You can use the raise hand feature in Zoom. If you're watching on Twitch, just type in the question in the chat box and we'll read it for you. Okay, any questions? Raise your hand. So could you remind us, in this last example you showed, what is the non-hermitian topology and what is its manifestation here?
So in this one, so basically this is non-hermitian topology because, so the manifestation is that only the oscillator on the edge starts oscillating. So even though, let's say in this setup, even though spin current is injected in every other oscillator, only the spin torque oscillator on the edge actually starts oscillating. Okay, so that's the result. Okay, so that turns out to be a result of non-hermitian topology, and the non-hermitian topology basically comes about because this system is a non-hermitian version of the SSH model. So if you inject spin current only on every other side, then if you do this right at the critical current for oscillation, then the damping is precisely staggered. So you have a negative damping here and a positive damping here that is precisely alternating, and this then gives rise to the non-hermitian topology basically. But I didn't want to say too much about it in detail because it's really kind of Benedetta's talk, and I don't want to repeat things that people can look back. But the non-hermitian topology is in the band structure of this SSH model. If you compute the band structure of that, you can assign topological invariants that protect the existence of this edge state, which then manifest as oscillations only of the edge spin torque oscillator.
So it means basically that it maps to a system with a non-hermitian Hamiltonian, is that?
Exactly, yeah.
Okay.
Yeah.
All right, so we have some questions. Dennis Candido, please unmute yourself. You can also turn your camera if you want.
Okay, thanks for the nice talk. I just want to make a quick question. So, is there already any experimental realization of the destructive interference between the two magnons that split at the ring with a spatial anisotropy dependence?
Not that I know of. So these let's say these structures like that have been made, but to let's say not from the point of view of making a geometric phase interference experiment or so. So that you can also manipulate the phases in other ways. So there are some experiments where the phases are manipulated with local fields, say. So by just making the fields that the spin waves feel on left and right slightly different, and you can also imprint the phase difference. But this is not necessarily a geometric phase. So to really imprint this geometric phase, that is not in this kind of setup with the ring that I discussed is not done as far as I know experimentally. Of course, there are kind of other manifestations of geometric phases of spin waves. So this was only like discussing a couple of examples. There are other manifestations. Maybe, so for example, Shuichi Murakami has been discussing a lot the manifestation of these phases in momentum space, where you can get anomalous transport. Let's say heat transport, for example, also due to similar phases.
And just another quick question related to that matter. What does control that gray area of the frequency where you don't see any spin wave propagation? There is a graph that you showed with a gray area.
Yeah, let me quickly go back. So this would be a good question. So there is a spin wave gap also, because there is anisotropy and fields here. So you need a finite frequency to actually excite spin waves. So that's what determines this gap here.
I see. So the larger the difference between the anisotropy, the larger would be this gap over here.
Not necessarily the larger the difference, but you're talking about this gap here, right? Where there are no.
Yes, exactly.
So that would also be there without anisotropy. But if you would only have an external field, say you would need to overcome. Let's say you would need to be above the frequency set by the external field. Okay, but here there are anisotropies, so here it's slightly different. Yeah.
Okay, thanks.
Okay, Mingzhang Wu, next question, please.
Very nice talk. I also have a question on this page. So if we consider a spin wave in this thin film ring, if we do not have any anisotropy fluctuation distribution, and we only have the demagnetization field to tilt the precession plane, do you think is that sufficient to realize this kind of phase?
Yeah, so let me be a little bit more precise. So in the calculation that we did, we just put in by hand that the anisotropy changes in the way that let's say, such that the ellipse of precession would rotate if you go around the ring. Now, what I'm saying is that already this, let's say, the shape of this ring and the shape anisotropy would already cause the ellipse of precession to change as you go around this ring. Maybe not precisely in the way that we compute here, but it would already give you some geometric phase that is related to the ellipticity, say.
Okay, thank you.
Yeah, so it's not it's not. I don't want to make the claim that if you make any ring like this, that you get precisely what we predict. But in principle, there are shape anisotropies that would do already part of the deal here.
Okay, thank you. Shen Fan, next question, please.
All right. Hi, Rembert. Thank you very much for the nice talk. I missed that in the, I think it's the second part of your talk, when you talk about the Hannay angle. I think you used the example that just a simple magnetization precession around that a field, but if you can also gradually rotate that field, then after it comes back, then this precession should have gain an extra phase. Very like a Foucault pendulum. So this seems to me is a rather straightforward experiment, because all we need to do is doing FMR while slowly varying the external magnetic field, and then after a while, after it comes back, and then just compare the phase with another control sample without moving the external magnetic field. Is that?
Yeah, I think actually the FMR is not going to work, because with FMR you actually imprint the phase on the. So with FMR you fix the phase of the precession by the FMR field. By the
driving field.
Yeah, exactly. So that's why I say that these time-dependent experiment, if you want to do this in a time-dependent way, it sounds easy, but I think the Gilbert damping would, so you would have to excite the magnet and then then just let it go basically, and then probably it damps out before you would observe the phase. You see?
This is sorry, you're talking about the driven FMR, or was this just the natural oscillation?
No, what I'm saying is that if you would do what you say, so if you would keep on the FMR field, so if you would continuously drive it, and then somehow all the time the phase of the precession would be locked to the phase of the microwave field, and so that wouldn't work. But if you would want to observe this particular phase, then you would have to excite the magnet once, let it precess, and then change the field. But then of course the precession will damp out, and then so that's why I think so. Then basically you have to be quicker than this time scale that's on the board here.
I see.
But you have to also be slow, because you have to be adiabatic. So I think that is probably very hard. So that's why I think that this spin wave interference is a little bit more promising.
I see.
Even more promising is this spin torque oscillator, because there, actually dissipation is there from the start and taken into account.
Right, but just a quick follow-up question. If we just drive it once and let it precess on itself, while we're tuning the field, it's very likely the frequency is changing when we tune the field. So is the phase still well defined in those cases? Even though I know when we come back, it's probably can still compare the relative phase, but in between.
Yeah, that's a good question. I've shoved that a little bit under the rug. So there. If you would do what you, so let's imagine that the damping is so small that we can do what you suggest.
Right.
Then let's say if you would only change the direction of field, then the frequency would be the same if there are no anisotropies.
I see.
But in principle, it might be that the field changes due to anisotropies or so, the magnitude of the effective field, I mean. And then you also get what people refer to as a dynamical phase. And what you would then have to do is actually, suppose this would all work, which I think is a big if, but let's suppose you would do that, then you would have to do, let's say, the field cycle. So looking at this picture here, you would have to go do the field like this, compare the phase, and then compare it with the field the other way around, and then add the two, and then basically only the geometric phase will survive somehow. So you can extract this geometric contribution there.
I see. Thank you.
Yeah, my pleasure.
Stefan Blugel, next question, please. Stefan, you need to unmute yourself.
Sorry, I muted myself a little bit too late. It was a very nice talk. I really appreciate talks where I learn a lot. I have one question. At the very beginning of your talk, you draw somehow a similarity between the Hannay phase and the Barry phase. In this later part of your talk, you discussed basically the classical dissipative system by Landsberg, which I would call kind of a non-adiabatic dissipative phase.
Yeah.
Is there a way back to the, so to say, to the quantum system if I start making my magnets smaller and say now they are quantum magnets?
So that's a good question. I don't. Okay, to be honest, I don't know. I would think that since for this particular phase by Landsberg, I think also, let's say, nonlinearities are also important in dissipation, and I think in quantum mechanics ultimately you deal with linear equations, so there's no obvious connection there. But I don't know. Maybe if you think longer, then there may be some connection, but I wouldn't know. But I would think it's not at all obvious in an obvious way related. Also, these let's say these Hannay angles are more related to Barry phases because they are both dealing with, say, adiabatic dynamics and Hamiltonian systems, say, and those are also completely unrelated to these Landsberg phases.
Right. Yeah. This connection I saw. I only was not clear to me how to go back, so to say, to the quantum system. But you get something new there if you have a dissipative quantum system or something like this. Yeah.
Yeah. So I think it's not obvious because somehow these Landsberg phases are more, let's say, really in dissipative nonlinear equations, which to me would only arise as an effective description, perhaps, of some quantum system, but are essentially classical.
Okay. Thank you very much.
Thank you.
Okay, Rolando Valdez Aguilar, next question, please.
Hi, thank you for a wonderful talk. So if we can go back to this issue of potentially detecting the phase with FMR, I think you could do this experiment actually by using like pulsed type FMR and doing a stroboscopic measurement, so that you control the phase of the excitation microwave field, and you put the magnetic field in whatever direction in your phase space here, and then you move the magnetic field, go back to the excitation. Essentially, you build the response. The measured response will be as a function of the position of this magnetic field. So this could potentially actually reproduce your calculation, as long as you have a coherent control of the phase of the microwave excitation.
Okay, yeah, so I think it's a good suggestion. I would have to think about it in more detail, say. Yeah, thanks for the suggestion.
Sure, no problem.
Okay, thanks. Here's a question from Twitch from Christian Binnick. The loop geometry reminds me somewhat of a Josephson junction where flux can penetrate only in flux quanta. I wonder if you apply a magnetic field to lift the destructive interference. Is that a sensitive stepwise transition between destructive and constructive interference, or is it smooth and continuous?
Yeah, thanks for the question. In this case, it would smooth and continuous because this let's say this phase is not purely it's not necessarily pi in this case. That it's if it's due to this ellipticity in this particular example that I discussed here, this phase is not necessarily pi, but is very dependent on precisely the anisotropy. So if you look at the expression here, there's a prefactor which depends on fields in a complicated way. And this phase is definitely not always an integer times pi or so not purely destructive, but other. And so it will also be removed, not in let's say a binary fashion.
I think you also showed another example earlier where it had a ring with a variable exchange along the ring.
Yeah.
So what about this case?
In this case, I believe so, yeah. So this case was actually only intended as a kind of the simplest. We have not even written this down, but
yeah. But I think you mentioned that you will go from so the destructive interference will persist as long as the contour encloses the origin.
Yeah,
right?
exactly.
So as soon as you move it away, it's no longer destructive. So
exactly.
in this case,
So
would there be like a jump in the transmission, or is it going to be broad?
I believe so, yeah, in this particular case. So this particular case is really like it really maps to a spin 1/2 Berry phase, because it's basically a two classical oscillator system, and in the spin 1/2 Berry phase also the Berry phase is gone as soon as you don't swipe anything. So I think in this case yes, but I would have well, I would have to think about it a little bit longer, but it would be more. Also, the interference is more destructive here, so here the phase difference is really pi to begin with. I mean, of course, this is all subject to Gilbert damping still. So Gilbert damping will make the interference not perfect to begin with. But okay, let's consider that a minor detail for now.
Okay, thank you. So I think we're out of questions. So let's thank Professor, actually, yeah, there's another one. Dmitro Bozhko, please go ahead.
Yeah, hello. Thanks, Rembert, for a nice talk. Actually, I have a question, pretty experimental one. So in this ring structure, what happens to the phase of wave when it's actually turning a corner? When the wave enters the ring? Have you considered any of those effects?
Let's say right, so there will definitely be also what people call dynamical phases. So there will also still be phases picked up just because of the details of the propagation here. But those are not, let's say, robust, so to say, and those will also not necessarily lead to interference. I mean, actually, in this other example that I showed, we don't consider spin waves coming in, but we consider more attaching electronic leads where you don't have this problem per se. Yeah.
Okay.
So this was so I've not to be honest, the answer to your question is I've not really considered that. So this was just an example that I want to highlight what you could in principle do with it. But I don't take this example very serious myself, to be honest. But I just thought it was neat.
Yeah. Thank you.
Thank you.
Okay, thank you very much for the nice talk.